Another type of the pendulum is called the physical pendulum, consisting of the rigid body with the mass equal to the m and the moment of the inertia equal to the I. So consider these pictures. Our rigid body with an arbitrary shape is hanged at this position. So this position can behave as the pivot, right? And then if we release the object will just oscillating left to right to left to right about this equilibrium position. So let's consider this video. So we have the rigid body as a rectangle. So if we release right, it just oscillates to left to right to left to right about this pivot here. So let's call the physical pendulum. So then again, in this case, we just want to study about this physical pendulum. We just want to find the angular frequency and then the period and the frequency. Okay, so let's say that if this position is the center of the mass of the rigid body, and if we have the distance from the pivot to the center of the mass is equal to the h here, we say that the center of the mass, right, is the point, the position that the force exerting on. So in this case, we have the mg. Okay, the mg which just exerts into this direction. So it's just the same as the simple pendulum. We just want to try to find the torque due to this mg, right? So then we can just break the component of the force mg into the two components. The one is in the radial direction and the other one is in the tangential direction. So we have this one for the radial direction, and we have this one for the tangential direction. So if angle equal to the theta, so this one equal to the theta as well. We have this component equal to the mg cosine theta, and this component equal to the mg times the psi theta. This component is going to go cancel out with the force due to the knot at the pivot here. Okay, so that's why we're going to consider only the mg psi theta. And then again, it's just exactly the same as we had done for the simple harmonic motion. The mg psi theta will produce the torque, right? That try to restore or try to move the object into the equilibrium position here. So then from equation, okay. So then from equation, right? If we consider the tangential component. Okay, if we consider the tangential component, we said that the net torque equal to the I and then times the alpha. So just keep in mind that this I, okay, this I is going to be moment of inertia of the rigid body about the pivot, not the center of mass. Okay, so let me just emphasize again. The I here is the moment of the inertia of the rigid body about the pivot. Okay, about the pivot, not the center of the mass. And then okay, so let's just plug in the net torque into this question. We have negative the mg times the psi theta. This one is for the force, and then times the distance of the pivot to the point of the action, right? So it's just equal to the h here, equal to the I, and then times the d square theta by the t square. Okay, again. So now we can just rearrange the equation. We can have the d square theta by the dt square, right? And then plus the mgh, and then over the I times the psi theta is equal to the 0. So actually we have seen this one already, right, from the simple pendulum. So we say that okay, we have the psi theta here, so it means that this question is not the simple harmonic motion. Again, for this one, right, it's not the simple harmonic motion. So we just want to change this into the simple harmonic motion. How? Then again, we need to use the approximation, right? So we say that if the theta is very small, then we can do some approximation. We can say that the psi theta here is about the theta. Okay, so then finally we have these equations. So we have the d squared theta over dt square, right, plus the mgh over the I theta equal to the 0. Then if we compare these equations to the fundamental equations of the simple harmonic motions, again this one, okay, so it means that the constant in front of this variable, right, is just equal to the omega. Then you can see that the things here, right, is just equal to the omega square. Then we can get the omega equal to the square root the mgh over the I, and then equal to the 2 pi times the frequency, and then equal to the 2 pi over the period t. Okay, so just keep in mind that the m here is to be the mass of the rigid body, the g is the 9.8, right, as usual, and the h is the distance from the pivot and then to the center of the mass. And now the I is the moment of inertia of the rigid body about this pivot, not the center of the mass. Okay, so now let's consider some examples. Okay, so for these examples, a physical pendulum consists of the disc. Okay, we have the disc here of the radius equal to the small r, right, and the mass equal to the capital M, the 500 gram, connected to one end of the rod of the length the 500 millimeter, and the mass is a small m, 270 gram, right. The other end of the rod is hang, okay, and is freely pivot, so it means that this is going to be the pivot in this case. So now for the part A, we just want to calculate the moment of the inertia of the physical pendulum about the pivot. Okay, so now, okay, for the part A, okay, so we just want to find the moment of inertia of the system, right? So we can say that the I of the system, let me just, simply just write out as the I, is equal to the moment of inertia of the rod, okay, and then plus the moment of inertia of the disc. So now for the rod, okay, moment of inertia of the rod is equal to what? So we have the pivot at one end, right? Then moment of inertia of the rod is just equal to 1/3 times the m, so the m here just be the mass of the rod, and then times the length of the rod square, so we have the L square here. So if you don't remember this equation, just try to review the rigid body part, okay, in the previous chapter, and then plus the moment of inertia of the disc. Actually, we have not only moment of inertia of the disc about the pivot, right, but sorry, about the center of mass here, but in this case the pivot is at this position, so it means that we need to shift moment of inertia from the center of mass here to be at this position. So which theorem should we use in this case? Let's think. Okay, we can use the Parallax theorem, right, to shift the moment of inertia about the center of mass to be the moment of inertia about the pivot here. So it said that moment of inertia at this position, right, is equal to moment of inertia about the center of mass. In this case, equal to the 1/2 times the capital M and then times the radius square, right? This is moment of inertia of the disk, okay? And then plus, okay, so now we need to shift from the same point to this pivot. So just plus the M and then times the distance between these two positions, right? It's just equal to the L plus the R. So we have the capital L plus the small r and then square, and that's it. So that's be the moment of inertia of the whole system here, equal to, okay, so now let's plug in the number as the SI unit. For the small m, right, the small m here is 270 gram. Okay, we can just change to kilogram to be the 0.270, and now times the L. The L is 500 nanometer. We can change to kilogram. We can change to meter as well. It's just 0.500 square, and then plus, okay, the 1/2, and then the mass of the disk, right, the 500 gram. So it's equal to 0.500, and then times the small r square. Small r is 10 centimeter, so it's just 0.100 square, plus now capital M, right, just 0.500, and then times the L plus the R. The L is 500 millimeter. We have the 0.500, and then plus the R is what, 10 centimeter. Okay, we have the 0.100 square, and then close bracket. So then after using the calculator, one would get that, okay, moment of inertia of the whole system here is going to be equal to the 0.205 kilogram and then times meter square, and that's it. Now for the part B, we need to find the distance from the pivot to the center of the mass. Okay, so now we just want to find the distance from the pivot to the center of the mass. So actually, let's say that we just want to find the position of the center of the mass, right? Then okay, how about, actually this pictures just look quite difficult to see. Let me just draw another one again. So let's say that everything is just aligned vertically like this. Okay, and we have the disk. Okay, something like this, right? So okay, so let's take a note that we have this distance equal to the L, right? And then we have the radius here equal to the R, right? So let's note that this is center of the mass of the disk, right? And then this position, okay, this position, which is the L/2, is center of the mass of the rod, right? Okay, so now we just want to find center of the mass of the whole system here. So which one should we use, right? Okay, so let's say that H, okay, H is the center of the mass of the whole system, equal to, okay, so it's going to be equal to the from equation, right, the m1 y1 plus the m2 y2, and then equal to the m1 and then plus the m2, okay, from the equation. So let's make number 1 to be the rod and number 2 to be the disk. So then here we have that it's going to be equal to, okay, the mass of the rod, right, it's just equal to small m, and then times the center of the mass of the rod. Okay, so it's just this position. Let's say that it's just equal to the L/2. Okay, it's just equal to the L/2, and then plus the m2 is the mass of the disk, which is the capital M, and then times the center mass of the disk, in this case just equal to the L and then plus the R, right? And then over the summation of both masses, so the small m plus the capital M. So now we can just plug in the number into these equations. Okay, oops. So then we have the small m, right, is equal to 0.270, and then times the L half. The L is what? The L is 500 millimeter, so the L half is the 0.250 meter plus the capital M. The capital M is the 500 gram, right? So we have the 0.500, and then times the L plus the R. The capital L is 500 and the R is 10 centimeter. So okay, we have okay, so we have not enough space. Okay, so we have the L is 0.500 and then plus the R is 10 centimeter, so we have the 0.100, and then over the sum of the both masses, 0.270 and then plus 0.500. Then finally the answer is 0.477 meter. So it should be somewhere about, okay, so the L here is what? L here is the 0.5 meter, right? So it should be somewhere here. Okay, so this equal to the H, and then this portion is the central mass of our system here. Now for the part C. Okay, now for this part we just want to compute for the period of the oscillation. Okay, so that's simple, right? We can pick period T, right? Then we can pick this one and this one to solve for the period. So we say that the 2 pi over the period equal to let's see, the square root the mgh and then over the I, right? Or we can get that the T, okay, the T equal to the 2 pi and then square root of the I over the mg times the h. Okay, so now let's plug in the number into the equations. Equal to the 2 pi and then square root. Now for the I, right, moment of nature of the system equal to 0.205, and the mass, okay, the mass of the whole thing here equal to 0.270 plus 0.500. Okay, so don't forget that this must be the mass of the whole rigid body. So it's just equal to 0.270 plus plus the 0.500 and then times the G, the 9.x0, right? And then times the h, the distance from the pivots to the center of the mass, right, equal to the 0.477 meter. Okay, so let me just rearrange first, and then finally, okay, we can use calculator and to get the answer to be 1.50 second.